Welcome to the Problemos channel, Season 2, Episode 3, the episode in which we will discuss the solution of the mathematical problem S2M3. Before we do that, however, please allow me to remind you that I have put together the Season 1 guide, which is a PDF file available from my free GitHub repository. And in that file, I have compiled the list of all the episodes that we produced during the first season, and for each specific episode I list the topics or the material that we describe in this episode and the name and the number of the mathematical problem that we formulate in that episode and the name of the number of the mathematical problem that we solve in that episode. The link to this PDF file and to the GitHub repository overall is in the description or in the comments section of this video. Feel free, be my guest. If you decide to teach mathematics or if you want to conduct a math circle, for example, you can use the material that we present on this channel, and the information that I have compiled in Season 1 guide should make your life easy in that respect. And if you do not want to teach mathematics or you do not want to conduct math circles, I hope that the material in that Season 1 guide will make your overall experience with this channel more pleasant, because the navigation through the material that we present on this channel should be much more straightforward with that season guide. If you are new to this channel and you have joined us recently, then we suggest, or it's a good idea, to watch our episodes in sequence, starting from Season 1, Episode 1. In this episode, we give several concise enough yet faithful enough definitions of what is mathematics. In Season 1, Episode 2, we explain how to practice mathematics correctly, and we also explain the difference between a mathematical exercise and a mathematical problem. It turns out that the process of doing a mathematical exercise does not require any ingenuity, creativity, or improvisational skills, and in contrast, the process of solving a mathematical problem does require quite a bit of technical ingenuity, creativity, and improvisational skills. And this is precisely the skills that we try to nurture and develop on this channel, and that is why we do not do exercises but only solve problems on this channel, problems in mathematics, theoretical physics, and computer science. In these episodes, we also learned that problems in mathematics can be solved not haphazardly, and these problems can be solved in a somewhat organized fashion by applying the so-called basic problem-solving approaches to the problem of searching for a solution of these problems. On the scale of guaranteed solution of a problem versus not guaranteed solution of a problem, basic problem-solving approaches sit on the opposite end of that spectrum with respect to the algorithms, because an algorithm, whether it's a mathematical algorithm or a computer science algorithm, is a finite description of a finite number of steps that guarantee that the problem at hand will be solved. And with a small wrinkle, a computer science algorithm also assumes that the problem will be solved without human intervention. On the other hand, the problem-solving approaches, which are formulated in a mathematical jargon-free language, they do not provide any algorithmic guidance, like an algorithm, for example, which is very saturated with a highly specific mathematical vocabulary. But on the other hand, problem-solving approaches bring front and center the fact that mathematics is an art of telling a story of how and why, and in order to generate that story as authors, we need to possess precisely the skills of creativity, ingenuity, and improvisational skills. And the process of applying this or that problem-solving approach to a process of searching for a solution of a mathematical problem precisely requires us to exhibit these specific skills: creativity, ingenuity, and improvisation. In the lightning round so far in Season 1, we have studied the so-called transform and conquer problem-solving approach and reinterpret and conquer problem-solving approach. According to the transform and conquer problem-solving approach, when we try to apply that approach to the process of solving a mathematical problem, we may look for a candidate transformation that possesses the following three fundamental properties. That transformation should be invertible or reversible. That transformation should preserve the technical essence of the problem at hand because we want to solve this problem and not another problem. And that transformation should provide us with a tactical advantage that will make the process of searching for a solution of a transform problem more tractable and more straightforward. Once a solution of a transform problem is obtained, to that solution we apply the reverse transformation and thus obtain a solution of the original problem. The close cousin of the transform and conquer problem-solving approach is the reinterpret and conquer problem-solving approach, but that approach is slightly more subtle, more delicate, and requires, in some sense, more intellectual finesse in its application, because not just in mathematics, but in any endeavor in life, sometimes it so happens that even a very small and very subtle change in perspective or in the angle of view on this or that problem may provide drastic positive results. According to the reinterpret and conquer problem solving approach, we are to look for a candidate reinterpretation of the local matter at hand that possesses the following two fundamental properties. That reinterpretation should, again, preserve the technical essence of the problem at hand because we want to solve this problem and not another problem. And that reinterpretation should, again, give us a tactical advantage that will make the process of searching for a reinterpreted problem more straightforward and more tractable. Usually, the way it works with the reinterpret and conquer problem-solving approach, once we obtain a solution of the reinterpreted problem, that solution pretty much or almost mechanically becomes the solution of the original problem, because the reinterpretation of the local matter is quite often spliced tightly into the original problem. We put together the playlist called Transform and Conquer that collects all the episodes in which we demonstrate slowly and thoroughly the mechanics of the application of the transform and conquer problem solving approach to the solution of mathematical problems. And that playlist, Transform and Conquer, can be found on the homepage of our channel. And likewise, all the initial episodes in which we explain how to apply reinterpret and conquer problem solving approach to solving mathematical problems slowly and thoroughly also form the reinterpret and conquer playlist, which you can also find on the homepage of this channel. And these playlists also should make your life and your overall experience with this channel easier. Starting with this episode, we begin the study of the so-called reverse order problem-solving approach. Very powerful, and with just these three problem-solving approaches, transform and conquer, reinterpret and conquer, and reverse order, quite a bit of damage in a good way can be done to the process of solving problems. Now, the reverse order problem-solving approach comes in two main flavors, which I call mechanical and heuristic. Mechanical and heuristic are my terms. Once you understand how the reverse order problem-solving approach works, feel free to give these flavors your own names, which you think are more appropriate. To the best of my knowledge, the ancient Greek mathematicians were aware in principle about the reverse order problem solving approach. Quite likely they, or perhaps they did not call it specifically that, reverse order, or sometimes reverse timeline problem solving approach, but in general, especially when it comes to Euclidean geometry, again, as far as I am aware, the ancient Greek mathematicians knew that some mathematical problems can be solved by applying the reverse order, or what we call these days the reverse order problem solving approach. So how does this new to us reverse order or reverse timeline problem solving approach work? Well, let's say we are given a certain problem. What's this? And the fact that we're given that problem, I will designate with some initial amount of material, and we will call it the problem. This is what's given to us. A traditional way of solving problems in mathematics and theoretical physics and computer science in a not so poetic um, way can be called a forward flow of causality, and that forward flow of causality works as follows. We take the material that's given to us in the problem statement, the material G, for example, as an input or as initial state, and then using that initial amount of material, we generate technically again a chain of implications if P then Q. For example, if what's given to us is true, then this and that must also be true. And if this and that is true, then so and so follows. And if so and so is true, then so on. And by stringing these implications together, eventually we will arrive, if the given problem, of course, has a solution, we arrive at the solved state. Now, let's say we model these implications with geometric points. So, for example, the forward flow of causality can be loosely portrayed as follows. This will be technical, let's say the first implication, then the next one, and then the next one, and the next one, and the next one. Somehow our implications dance around. I will depict the forward flow of causality with the corresponding arrows, like so. And at some point, there will be logically the last implication in our chain. And if each and every implication is correct, and we haven't made a single mistake anywhere, then it follows that by the time we arrive at the logically last implication, we arrive at a solution of the problem. Roughly, let's say, it doesn't have to be specifically that way, but for the purposes of this discussion, let's say we can roughly partition the problems in mathematics as problems to prove and problems to find. In either way, the last implication will be either the last step of the proof or the last step of a certain computation that brings overall the problem into a solved state. This picture here represents a traditional or normal or usual forward flow of causality. So how does the reverse order problem solving approach, both of its flavors, mechanical and heuristic, work, and how do they arrive? Well, both flavors of the reverse order problem solving approach arrive from a perhaps somewhat loose and somewhat vague idea of recording with a movie camera the process, let's say, that unfolds in a given problem, or the sequence of events that unfold in this particular problem. Again, here we begin with something that is given and something that represents the end or the final solved state of the problem. Usually we watch our movies in a forward flow of causality mode, so to speak, from the first frame of the movie to the next one, next one, next one, all the way to the last frame. Here, however, an interesting notion comes in that we know is quite powerful, deep, and useful in both mathematics and theoretical physics. It's called symmetry. And whether this presence of this symmetry is guaranteed in this situation or not, this is a topic for a separate discussion. I do not want to pollute our discussion right now with the details that may not matter. So let's say, for example, through the application of symmetry, it so happens that it is possible to, according the reverse order problem solving approach, begin not at the beginning the first or not solved state of the problem, or not from the first frame of the movie, but from the last frame of the movie, and watch that movie in reverse order or in reverse timeline or backwards, so to speak. Then let us say I will depict these guys with yellow color. Again, we will portray the implications with geometric points of yellow color, and it may so happen that we may be able to string together a sequence of implications that will take the final state or the solved state as its input, as its initial point, and will dance around, zigzag this way and that way, and eventually terminate with what is given. In this description, flow this way, in this description of the reverse order problem solving approach, we make technically an assumption that the problem at hand does have a solution. Pedantically, in the vacuum, we do not really know if a problem does have a solution or not. Consequently, in this case, our assumption that a problem does have a solution is not based on any material evidence and is admittedly somewhat arbitrary. However, in our defense here, we think and act like a mathematician, and we wrap our description of the reverse order problem solving approach into the language of if. If a given problem does have a solution, then it means that eventually it will be found in the solved state. And for the purposes of the application of the reverse order problem solving approach to the process of solving a problem, we make that assumption, like I said, somewhat blindly, and we're not interested in exactly how it was solved. That is perhaps one of the key steps in the application of the reverse order problem solving approach to the process of searching for a solution of a problem. Initially, we do not care how that solution was generated and how the solution was obtained. For all we care, an all-knowing mathematical wizard, if we represent a problem as, for example, a jigsaw puzzle, have put the pieces of this jigsaw puzzle, just to give you a mental image here. Such an all-knowing mathematical oracle has arranged all the pieces of the jig puzzle together and handed over to us here. The problem is solved magically. Now, using that solved state or the final state of the problem as our input or as a fodder, we make our best to generate a sequence of implications that begin at the solved state or at the final state and then wind their way towards what is given. The idea next of applying the reverse order problem solving approach to the process of a search for a solution of a mathematical problem is that the process when we were able to generate these implications and solve the problem backwards or in reverse order may, there are no guarantees here, but that process may give us enough tactical material or immediately actionable material that may again allow us to say, if things work backwards this way, then forward, in forward flow of causality, these very things should work this way. Consequently, if again we were able to successfully solve the problem in reverse order and generate some number of implications that terminate with what's given, we may flip that reverse flow of causality, and we may be able to generate another, technically this will be different implications, and we may be able to generate another chain of implications that will allow us to solve the problem in forward flow of causality. And I will depict this forward flow of causality with the arrows that run this way. Now, this way, this way, this way, and boom, problem solved state. And when we think about a way to generate this forward flow of causality, or the chain of implications that solve the problem in a traditional way, we use the implications or the steps or the material that we were able to unearth and uncover during the solution of the problem in reverse order as guiding landmarks, or as lighthouses that shine brightly in the night sky, or we logically or vaguely speaking, we use these implications as stepping stones that will help us to generate the forward flowing solution of the problem at hand. Now, the mechanical flavor of the reverse order problem solving approach works well with mostly computational problems, or with problems in which certain process takes place, and then we are inquired about what was, for example, at the beginning of the problem or at the end. The heuristic flavor of the reverse order problem solving approach can be applied to any type of the problems, computational or non-computational, and with non-computational problems, the application of that problem solving approach does require sometimes significant powers of perspicacity from us, because the process of seeing what is really going on from the solved state and winding our steps to the initial condition in the problem may not be that obvious. So we will, over the next several episodes, we will cover both flavors, but we will begin with the mechanical flavor of the reverse order problem solving approach, because it's easier to grasp. Admittedly, all of this sounds very abstract, and it does require us to think at a higher plane of abstract cognition, but do not worry, I'll go over that explanation in the next episode as well. But initially, we will start with something more straightforward, more easier or simpler. We'll start with the mechanical flavor of the reverse order problem solving approach, and once we get the hang of how things work with the mechanical flavor, we will move on to the heuristic flavor of the reverse order problem solving approach. As such, let us address the meat and potatoes of the problem S2M3. As a reminder, in that problem, we were given some number of swans, represented here with NX, that approach a set of lakes. And over each and every flake, one and the same process unfolds. Half of all the swans that are approaching that lake, plus half a swan, land on that lake, and then however many swans stay in the air, they move on to the next, fly towards the next lake. And once they get to the next lake, over that lake, the same process unfolds and repeats itself. One half of all the swans that approach that lake, plus half a swan, land on that lake, and however many swans remain in the air, these guys fly towards the next lake. And the question in this problem is, what is X? How many swans were in this flock if all the swans landed across 7 lakes? This little problem is interesting in several respects, because on the one hand, for example, the language of this problem is extremely simple. It's not even my favorite proverbial middle school. This is most likely even pre-middle school vocabulary. There are absolutely no kernels of group homomorphisms. There are no residues of holomorphic functions. There are no Laplace transforms. There are no differential equations and partial derivatives. There are no quadratic residues, no field extensions, no fields of characteristic 2, and so on. Very simple, very plain English, yet a particular formulation of this problem, especially this guy plus half a swan, is interesting because it tells already quite a bit about why it is also difficult to teach mathematics. Every time I give this problem to the indoctrinated students, then they see what's going on right away. Every time I give this problem to not so indoctrinated people, some of these people at least make an effort to think before they complain. And pretty much all non-indoctrinated people, which means pretty much, unfortunately, most or all the grown-ups, they start complaining about this piece, this clause right here, half is one. Roman, you are crazy. What's going on? Half is one? How does that work? That's impossible. You're giving us some nonsensical question. This is not real. Well, let us see if this clause makes sense or not. It should be understood that 7 in 7 lakes, of course, I used for demonstration purposes. I could have used 31, 59, 140, or whatever number of lakes whatsoever. But for the purposes of dealing with this clause, this number is very difficult. Even 3 is a complicated number. Let's just start with 1. 1 lake, 1 swan. 1/2 of 1 is 1/2. Plus half is 1 comes out to what? Comes out to precisely 1 swan, and 1 is a nice integral whole positive number, so things are good. Things make sense over here. All right, very well. Let's say 2 swans approach lake 1. How many swans will land on this lake? 2 over 2, 1/2 plus 1/2. This will be 1 plus a half. This will be 1.5 swans. That does not make sense, and mathematicians do not like dealing with things that do not make sense. And number 2 is unacceptable. And now let us analyze a much more complex or much more difficult number, 3. So what's going on with 3? Let's say 3 swans approach lake number 1. How many swans will land on that lake? Well, 3 over 2 will be 1.5 plus 1/2 comes out to 2. 2 is a nice whole positive number, nice integral number, so things make sense. And if we carefully analyze more and more consecutive numbers in that fashion, we will see that in this problem, the number of swans must necessarily be odd. With odd number of swans, things look good, they make sense, everything is fine. So once we get over the psychological barrier of this strange, perhaps, formulation half as 1, we can actually address the essence of the problem at hand. So how this problem can be solved? Technically, yes. We may try to solve this problem in a traditional or forward flow of causality. For example, let x be the number of swans that approach the set of lakes. Then over the first lake, how many swans landed? Well, we're told half of all the swans plus 1/2 landed on the first lake. And then how many swans then remained in the air? Well, it will be the difference between the number of swans that approached the first lake, x, and the number of swans that landed there. By the looks of it, this will be what? X over 2 minus 1/2. This is the number of swans that flew towards the lake number 2. And over the lake number 2, what happened? 1/2 of these swans, so 1/2 of x over 2 minus 1/2 plus half as 1 landed over the second lake. And how many swans remained in the air? Well, that the difference between the number of swans that approached that lake, the second lake, x over 2 minus this horrible number right here. That is the number of swans that flew towards the lake number 3, and so on. In theory, again, given enough paper and patience, we may keep constructing more and more convoluted and cumbersome equation, and maybe we will not any mistake anywhere, and we may arrive at an answer. using a forward flow of causality. But personally, when I look at this just couple of these attempts, that already sends the chills down my spine. This whole thing makes my liver quiver, and there has got to be a better way, in the sense that a way that is less computationally intensive and a way that is less error prone. And luckily enough, there is such a way, and that way is represented by the mechanical flavor of the reverse order problem solving approach. So how would we apply the mechanical flavor of the reverse order problem solving approach to our problem S2M3? Well, as we explained earlier, the reverse order problem solving approach prescribes that we make an attempt to start not at the initial state of a process that unfolds in a given problem, or not from the not solved state, but from the last state of the problem. In this case, that means what? Let's say as our swans flew across 7 lakes, some of them landed, some of them flew forward. We made a movie of swans doing their thing. And now, instead of watching that movie from the first frame to the last frame, we, as the reverse order problem solving approach prescribes, do not rewind our movie and jump right to the last frame of that movie and begin solving this problem from the final state of this problem. And what would we see in the last few frames of that movie? Well, we will see that in reverse order again, somehow in funny way, some number of swans took off from that lake in reverse order, which means that in the forward flow of causality, or in the traditional forward flow of time, some number of swans landed on the 7th lake. Now, what kind of tactical information can we extract from this situation already? At the risk of overloading this discussion with too many technical details, please allow me to mention another useful skill in mathematics, and that skill is the art and science of introduction of auxiliary objects. That art and science and the skill of introducing the right amount, placement, the quality of auxiliary objects when we solve problems will come with time and experience, but somehow younger students of mathematics feel that they can only work in a given problem with what they're given. In some sense, it is true, but as problem solvers, we actually enjoy a fair amount of freedom of bringing other helpful or auxiliary objects into the solution of the problem that do not shake or that do not perturb our problem too much. What type of an auxiliary object can we introduce in this case? Well, let me use the green chalk over here. In order to make the solution or the process of solving this problem more straightforward and not as difficult and not as convoluted, let us introduce the lake number 8. Yes, technically in the problem statement we are not given the lake number 8, but again, as problem solvers we enjoy a certain degree of freedom, and in order to make the process of searching for a solution of the problem more straightforward, more tractable, we can perfectly introduce the lake number 8, and we can refer to it, if you want, a virtual lake that is not given, but we place it here anyway. What does the introduction of the virtual lake number 8 buy us? Well, as the reverse order problem solving approach prescribes, we examine the last few frames of the swans flying and landing movie, and what do we see? We see that, let's say, x sub 7 swans approach that lake. And we're also told that all the swans land across 7 lakes. What does that mean? It means that 0 swans fly towards our virtual lake number 8. That is perhaps one of the first tactical observations that we can make by exercising the auxiliary object that we introduced over here, the virtual lake number 8, and the mechanics of the reverse order problem solving approach when we looked at the last few frames of the corresponding movie and we said, aha, 0 swans flew towards the lake number 8. And what does it mean tactically? How we convert this observation into actionable material? Well, if x sub 7 swans approach the lake number 7, then we know how many swans landed there. How many? X sub 7 over 2 plus half a swan in parens. And the difference between the number of swans that approached the lake 7 and the number of swans that landed there must be what? Must be 0. This is as straightforward, I hope, as straightforward gets. So this difference must be big fat 0. Can we solve this equation? Yes, some of us can solve this equation in our mind, but for the benefit of the audience, what do we do here? We multiply this equation through by 2, and what do we have? 2 times x sub 7 minus, carry 2 is into parentheses, x sub 7 plus 1 equals 0 times 2 is 0. We open up the parentheses, 2 times x sub 7 minus x sub 7 minus 1 equals 0. That maneuver should be, all these maneuvers should be straightforward. And now we see that 2 copies and 1 copy of x sub 7 cancel out. So 2 is gone, this guy is gone. And what do we get? X sub 7 equals 1. Wonderful. By manipulating in a not so computationally intensive way the constructed equation, also literally not having too many chances to mess things up and to make a mistake, we realize that 1 swan approached the lake number 7. You guys can rewind this segment and look at it again. Meanwhile, we will record this find in a concise and compressed manner with the letter A. A for the number of swans that approach the lake number 7. So the lake number 7 will be designated here. Out of the set of 7 lakes will be 1. Very well. According to the recipe of the reverse order problem solving approach, we should take the step of the movie that we watched here as done and move on to the previous frame or to the previous state of the problem. If we watch that movie again in reverse order, what will we see? Well, let's say this is lake number 6. If we watch that movie in reverse order, we'll see in some funny way backwards, some number of swans take off from the lake, which means that in the forward flow of time or in traditional time flow, the some number of swans land on lake number 6. Let's say that will be x sub 6 as the number of swans that approached the 6th lake. How many swans landed on that lake? Well, it's half of all the swans plus half a swan. That is how many swans landed on the 6th lake. And how many swans remained in the air after that maneuver? Well, the number of swans that remained in the air after that maneuver is equal to the number of swans that approached the lake number 7. And we already recovered that number. It's right here. So this difference between the number of swans that approached the 6th lake and the number of swans that landed there must be what? Must be 1. Beautiful. We have another straightforward equation which we know how to solve. We multiply this equation through by 2 times x sub 6, and we open up the parentheses right away. Minus x sub 6 minus 1 equals 1 times 2 equals 2. Again, we see the wonderful miracle of 1 copy of x6 canceling with the other. Only 1 remains, so x sub 6 equals to what? 2 plus 1, 3. x6 is 3. So here we record that fact. Let me erase this. You guys can rewind if you have to. We record that fact that number of swans that approached the lake number 6 out of set of 7 is equal to what? 3. And as the reverse order problem solving approach prescribes, we keep moving backwards in time and we watch the next previous several frames of our movie. And what do we see? We see that some number of swans backwards take off in a funny way from the lake number 5. That means what? That means that if x sub 5 is the number of swans that approached the lake number 5, then how many swans landed there? Well, we're given the recipe. X over 5, half of all the swans plus half a swan landed on that lake. And how many swans remained in the air after that maneuver? The number of swans that remained in the air after that maneuver is equal to the difference between the number of swans that approached the 5th lake and the number of swans that landed there. And that number is equal to the number of swans that approached the lake number 6. But we already recovered that number. It's number 3. So we write down confidently 3. And again, we obtain an equation that can be solved in a straightforward manner. Multiply this guy through by 2. 2 times x5 minus, we bravely open up the parentheses, minus x sub 5 minus 1 equals what? 3 times 2 is 6 equals 6. x5 and x5, 2 copies and 1 copy cancel out, and we discover that x sub 5 equals what? 6 plus 1, 7. So now we know that the lake number 5 was approached by 7 swans. How many swans landed there? 3.5 plus 1.5, 4 swans landed there, and 3 swans flew towards the lake number 6. Beautiful. Everything converges, so to speak. Everything makes sense. We didn't make any errors. We didn't make any mistakes. We record that fact that the number of swans that approached the lake number 5 out of set of 7 equals to 7. More of the same as the reverse order problem solving approach prescribes. We keep watching our movie of swans flying, landing, and flying in reverse order or in reverse timeline. We watch the next previous 2 frames, and what do we see? We see some number of swans in a funny way backwards taking off from the lake number 4. That means that in the forward flow of time, for example, x sub 4 swans approached the lake number 4. How many swans land there? We have a recipe. X sub 4, half of all the swans, 1/2 of all the swans, plus half a swan, land on the 4th lake. And how many swans will remain in the air after that maneuver? After that maneuver, the number of swans that will remain in the air will be equal to the difference between the number of swans that approached the lake number 4, x4, and the number of swans that landed there. And that many swans flew towards the lake number 5, and we computed that number already. That number is 7. Again, we obtain a straightforward equation, which we quickly solve by multiplying it through by 2. 2 times x sub 4 minus, we open up the parentheses bravely, x sub 4 minus 1 equals 7 times 2 is 14. Again, miraculously, 2 copies of x4 and 1 copy, negative copy of x sub 4 cancel each other out, and we obtain the answer for x sub 4, 14 plus 1, 15. So we write down that the number of swans that approached the lake number 4 out of set of 7 is equal to 15. And we erase this, making room for the next iteration. Here, I hope that our viewers now are getting on with the program. As the reverse order problem solving approach prescribes, we keep moving towards the initial state or unsolved state of this problem. And now we watch the previous few frames where some number of swans take off backwards in a funny way from the lake number 3, which means that in the forward flow of time, if x sub 3 is the number of swans that approach the third lake, how many swans landed there? Well, half of all the swans, x sub 3 over 2, plus half a swan, that's how many swans landed on the third lake. How many swans remained in the air after that maneuver? After that maneuver, the number of swans that remained in the air is equal to the difference between the number of swans that approached the third lake and the number of swans that landed there. And that means that many swans flew towards the lake number 4. And how many swans did it? We already computed this number. That's 15. Again, the solution of this neat little equation should cause no problem. We'll multiply it through by 2. 2 times x sub 3 minus, we open up the parentheses, x sub 3 minus 1 equals 15 times 2 is 30. Again, 2 positive copy, 1 negative copy of the same variable cancel each other like so. X sub 3 equals 30 plus 1, 31. So now we know that the third lake, the lake number 3, was approached by how many? 31 swans over the set of 7 lakes. More of the same. As the reverse order problem solving approach prescribes, we keep watching our movie in reverse order from the last frame towards the first frame. And what do we see? We see that in a funny way, in reverse order, some number of swans take off from lake number 2 this way. But in the forward flow of time, that means that some number of swans approach that lake. Let that number be x sub 2. How many swans land on that lake? Well, we have the recipe. X sub 2 over 2 plus 1/2. And how many swans will remain in the air after that maneuver? After that maneuver, the number of swans that will remain in the air will be equal, evidently, by the difference between the number of swans that approach that lake, x sub 2, and the number of swans that landed there. And how many swans in that case will fly towards the lake number 3? We already recovered that number, 31. There we go, 31. Again, we solve this equation by multiplying it through by 2. 2 times x sub 3 minus, x sub 2 minus x sub 2 minus 1 equals 31 times 2 is 62. 2 positive copies of x2, 1 negative copy of x2 cancel each other out. X sub 2 equals to what? 1 plus 62, 63. 63 swans approached the lake number 2, so we'll write it down over here. Out of 7 lakes, the second lake was approached by 63 swans. And finally, after eating almost all of our popcorn and drinking all of our soda, we now see, we're approaching the very first frames in our movie. And what do we see in these frames that we watch in reverse order? Well, some number of swans in a funny way take off backwards as we watch the movie in the reverse timeline order, which means that in the forward flow of time, x or x1, let's say, to be consistent, x1 swans approach the lake number 1. How many swans land there? Well, x sub 1, 1/2 of all the swans plus half a swan landed on the first lake. And how many swans remained in the air after that maneuver? After that maneuver, the number of swans that remained in the air is equal to the difference between the number of swans that approached that lake, x sub 1, and the number of swans that landed there. And that number is equal to the number of swans that flew towards the lake number 2. That number was computed by us in a straightforward manner, 63. And what do we do here? Multiply this guy through. 2 times x sub 1, open up the parentheses right away, minus x sub 1 minus 1 equals 63 times 2, 126. 126, 2 positive copy of x1, 1 negative copy of x1, cancel each other out. Add 1 to both sides of the equation. What do we have? 127, ladies and gentlemen. 127 swans approach the first lake out of set of 7. 127. And that number represents the answer to the problem at hand, which we solved by applying the mechanical flavor of the reverse order problem solving approach. One more time, we pretended that as the problem unfolded, or as the process described in this problem unfolded, we recorded the process of swans splitting in half, landing, flying forward with a movie camera. Then, instead of rewinding that movie and watching it from the first frame towards the last frame, we kept it there. We started looking at the last frame. We introduced the auxiliary object lake number 8 to make our reasoning more straightforward, because now we can have easy numbers to, or straightforward numbers to latch on. And by watching that movie in reverse order, we gradually computed the number of swans that approached the lake number 7, lake number 6, 5, 4, 3, 2, 1, and we obtained the answer to the problem S2M3. Beautiful. Now, recall that while solving problems using the Reinterpret and Conquer problem solving approach, we realized that there is more to mathematics than meets the eye, and that every worthy mathematical problem can be represented as a sort of dovetail join of two things: the material that does not change, or the material that represents the technical essence of the problem at hand, and the material that does change, and as such represents the irrelevant minutiae, the variance of which, by definition, does not affect the material that does not change. In this specific problem, what material represents the technical essence of the problem, and what material is an irrelevant minutia? Well, before we answer that question, let us try to capture maybe formulaically what is going on here in a not so brutal numerical way. Can we discern a certain pattern in these numbers? Here we have to be careful. In general, in vacuum, if we're given a finite sequence of numbers, let's say real numbers, as for example these numbers 1, 3, 7, 15, 31, and 63, and 127, 7 numbers, the next number can be made literally anything that we want. If we want, we can make the next number negative 19, for example. It doesn't matter. But because in this particular case we constructed or witnessed the mechanics of how these numbers form, then we can formulaically claim that the number of swans out of set of 7 lakes that approach the lake number k is given how formulaically? Perhaps a simplest formulaic description of this number will be a certain power of 2, in this case will be 7, minus k plus 1 negative 1, with k varying between 1 and 7. In other words, the numbers of swans that approached each lake is a sort of short perfect power of 2. 128 minus 1, 64 minus 1, 32 minus 1, 16 minus 1, 8 minus 1, 4 minus 1. Then how many swans land on the kth lake? Well, that question is easy to answer. We're given a perfect recipe. So the number of, let's say we represent the number of swans that land on the kth lake with uppercase L, sub k for the lake number, and outer set of 7 lakes. will be what? It will be the number of swans that approached that lake times 1/2 2 to the minus first plus half a swan 2 to the minus first. And doing straightforward arithmetic, what do we see? 2 to the minus first power will eat the 1 power of 2 in this term, and it will become negative 2 to the minus first. So we'll have 2 to the power of 7 minus k negative 2 minus 1 plus 2 to the minus first power. These guys cancel each other out, and hence, what does it mean? It means that the number of swans that land over the kth lake out of set of 7 is given by 2 to the power 7 minus k, with k varying between 1 and 7. And again, it should be evident that as long as we take any other whole positive number, the situation will be the same. I picked 7 just for demonstration purposes to show how the reverse order problem solving approach can work. So we can write down that, for example, if we're given n lakes, where n is a whole positive number, which varies 1, 2, 3, 4, 5, and so on, the number of swans that land over the that approach the kth lake out of set of n will be 2 to the power of what? N minus k plus 1 minus 1, with again k varying between 1 and n, the number of swans that approach the kth lake out of set of n, and the number of swans that land on the kth lake out of set of n will be 2 to the power of n minus k, with k varying between 1 and n. This is our description in symbols, slightly more formally. So by looking at these numbers, what do we see, and what represents in this case the technical essence of the problem, and what is the irrelevant minutia? Well, it should be evident that, let me erase this information here to make room for our next answer. It should be evident that the technical essence of this problem is the following iterative process, where we begin with a short perfect power of 2. For example, we begin with 127, which is what? 2 to the 7th power minus 1, and we represent this number as 64 plus 63. Again, this is a perfect power of 2. This is an almost perfect power of 2. So if we add 1 to this string of numbers, then we'll get 64 plus 64. 2 to the 6th plus 2 to the 6th becomes 2 to the 7th power. And we take this number, which is again almost a perfect power of 2, and apply to it the same string of operations, 63, which can be represented as 2 to the 6th minus 1. We represent it as what? 32 plus 31. Again, with 1 added, perfect power of 2, plus 1, 32, perfect power of 2, 2 to the 5th plus 2 to the 5th becomes 2 to the 6th. We grab this number, 31, represented the same way. We say that it is what? 16 plus, let me see, that 31 is 2 to the 5th minus 1, representable as 16 plus 15. Here again, we grab the number 15 and claim that this is 2 to the 4th minus 1, and represent that number how? As 8, a perfect power of 2, plus 7, a short perfect power of 2, and to the number 7 we apply the same maneuver. We represent it as what? As 2 to the 3rd, 8 minus 1, 7, And this is representable as what? 4, a perfect power of 2, plus 3, right? 3. And finally, to the 3, we apply the same maneuver. It's 2 squared, 4 minus 1, and this is representable as 2 plus 1. In our case, one swan approached the the 7th lake. 2 swans landed over the 6 lakes. Over the 6th lake, 3 minus 2, 1. 1 swan flew towards the 7th lake. But essentially, this iterative process of playing beautiful games with the decomposition of an almost perfect power of 2 in, for example, this direction represents the technical essence of the problem at hand and the language of swans approaching lakes is irrelevant minutia. By now we understand through the wisdom of the reinterpret and conquer problem solving approach that this specific process that remains the technical essence or the technical core of this problem or the core material around which this problem was built will remain invariant, will not change, and we can throw just about any reasonable vocabulary against that particular process. For example, let's say some number of people left the office and they went to have lunch. Every time that group of people approaches a set of restaurants, this one and the same process ensues. One half of all the people plus half a person enter the restaurant to have lunch, and however many people remain move on to the next restaurant. And as they approach the next restaurant, the same process unfolds. One half of the remaining group of people plus half a person enter the restaurant to eat lunch, and the remaining people move on to the next restaurant. So in that way, all the people in the group ate their lunch across 1, 2, 3, 4, 5, 6, 7, 29, 15, whatever number restaurants, how many people were in that group. Likewise, instead of swans flying over lakes and people eating lunch at restaurants, we can use the words of, for example, flowers being planted in the flower beds, cars parked across parking lots, books distributed across book shelves, or for example, gold coins being positioned or placed into jewelry boxes. That language will not change the essence of the process that we described over here, but it will give a different flavor. And as you understand, we suggest that our viewers come up with their own vocabulary or come up with their own way to describe this particular process with the language other than the language that we presented in this segment. This is it for the solution of this problem. We will now move on to the next challenge. Our next challenge will be the mathematical problem S2E3, which I titled The Devil and a Loiterer. In this problem, the devil spotted a loiterer, or a person who was not really doing anything useful. The devil approached the loiterer and said, listen, every time you cross this bridge over here, let's pretend that this is a bridge, this is the land, this is some water mess. So the devil tells the loiterer, every time you cross this bridge over here, the amount of money in your pocket will triple. The loiterer perhaps realized who he is talking to, so he asked in return, what's the catch? To which the devil replied, well, after the money in your pocket triples, you just give me my little cut of $27. The loiterer, not knowing any better, decided to make a deal. He made a deal, and after he crossed the bridge 3 times, he was left with no money in his pocket. And the question is, how much money did the loiterer have originally? One more time, the devil approaches a loiterer and says, listen, every time you cross this bridge, the money in your pocket will triple. The loiterer says, what's the catch? The devil says, every time that the money in your pocket triples, you just give me my cut of $27. So the devil's cut is, let's say, 27 bucks. 27 bucks. And in any direction, for example, in this direction or in that direction, whether the loiterer crosses the bridge this way or that way, it doesn't matter. The amount of money in the loiterer's pocket triples. In other words, becomes 3 times as large. And after 3 such crossings, 1, 2, 3, the loiterer was left without any money. There was $0 in his pocket. And the question is, how much money did the loiterer have when he agreed to this particular deal? By the placement of the problem, it is evident that this problem can be solved using the reverse order problem solving approach, the mechanical flavor of it. And for a top-notch job to make sure that our viewers understand how these things work, we suggest that you solve this problem both in the forward flow of causality or in the forward traditional flow of causality, and also in reverse order. Later on, once we understand how the mechanics of various problem-solving approaches work, I will, of course, not hint or not even explain which problem-solving approach can be used in order to solve this or that problem. And that is precisely the value of this practice, because when we try to solve a mathematical problem that way, we put our mind into a mode that is faithfully close to the mode in which the mind of a practicing mathematician operates, and that is the whole purpose of these exercises. This is it for this episode. Thank you very much for your time. Thank you for watching. I'll see you in the next episode, in which I will discuss the solution of the problem S2M4.